For decades, we drew the Milky Way too small. The maps, the numbers, the textbooks, all wrong. Our galaxy isn't 100,000 light-years across. It's twice that, maybe even more. We've been living inside a giant we never fully saw, a home far larger than we dared to measure. New technology has pulled back the veil, revealing a truth that rewrites nearly everything. How we chart the cosmos, when Andromeda will collide with us, and what that means for our place in the universe. This is not just an update. It's a revelation, the moment astronomy realized it had underestimated home itself. Leave a like and subscribe to the channel if you enjoy the content, as tonight we venture into these mysterious discrepancies in measurements. We begin. Open your astronomy textbook and turn to the illustration of the Milky Way. That graceful spiral labeled neatly with a span of 100,000 light-years across. It's wrong. Entirely wrong. Not slightly off. Not outdated by mere percentages. Wrong by nearly double. Every classroom chart, every documentary animation, every Wikipedia diagram you've relied upon portrays a galaxy only half its true size. For years, scientists suspected something didn't add up. Yet the evidence arrived in fragments, subtle hints, unexplained irregularities in motion, stars accelerating too fast along the outskirts, companion galaxies swinging too far from expected orbits, mathematical inconsistencies that refused to reconcile. Then came the deluge of data. Gaia's precision tracking, James Webb's deep field imaging, radio arrays charting hydrogen gas at the periphery, all pointed to the same revelation. The Milky Way stretches far past its presumed limits. It wasn't carelessness that led astronomers astray, it was perspective. We've been attempting the impossible, measuring a galaxy from within. Picture standing in downtown Manhattan, trying to sketch the boundaries of the entire city. You can't see the edges. There's no vantage point beyond. You are engulfed by skyscrapers, lights, and noise. That's our predicament. Nestled within a spiral arm, 26,000 light-years from the core, submerged in dust and starlight. For decades, astronomers used a straightforward approach. They observed the brightest stars in every direction, marking where their numbers faded. That fading line became the supposed boundary, 100,000 light-years across, neatly closed. But reality is never so tidy. Galaxies don't end like solid disks. They dissolve into faint streams and wisps. Stars drift outward in delicate threads, and clouds of gas fade into the dark. Beyond it all, dark matter, unseen but immense, extends much farther. Those early measurements captured only what glowed, never accounting for the vast halo that envelopes the Milky Way like a ghostly shroud. Everything changed when scientists began tracing stellar streams, cosmic rivers of stars ripped from ancient dwarf galaxies long devoured by our own. These star streams arc through space like relic trails, marking the invisible contours of the Milky Way's gravity. When these were charted, their paths extended well beyond the supposed frontier, 200,000 light-years, perhaps even more. The Milky Way is no modest spiral. It's a colossal titan. For ages, we've been measuring a shadow, not the structure itself. This revelation reshapes far more than textbook figures. It redefines our grasp of galactic dynamics. It alters predictions for our eventual collision with Andromeda. It doubles the search space for habitable worlds. Every equation resting on the old assumptions now fractures. But the most unsettling question remains. If we misjudged our own galaxy so drastically, what else are we wrong about? How many others are giants masquerading as dwarfs? Imagine this: you stand blindfolded in the middle of the Sahara Desert. Your task: measure the desert's total size. You can't remove the blindfold, can't use instruments, can only feel the sand underfoot and hear the endless wind. How accurate could that map possibly be? That's the plight of astronomers measuring the Milky Way. We orbit an average star in an outer arm, surrounded by curtains of dust that obscure nearly every direction. The galactic center hides behind immense walls of gas and debris. With optical telescopes, we see perhaps 10% of the whole. The remainder resides in wavelengths of radio, infrared, and shadow. By contrast, measuring Andromeda is child's play. It sits 2.5 million light-years away, its full disk visible in a single frame, spiral arms, core, and halo in plain view. We can photograph it, trace its structures, and count its clusters. Measuring the Milky Way, though, is like trying to capture your own reflection without a mirror, standing in mist. Early astronomers did all they could. The tools were light itself. They used Cepheid variable stars, whose rhythmic pulsing revealed distance. They calculated the positions of globular clusters, ancient star swarms orbiting the core, piecing together a map one uncertain fragment at a time, like assembling a puzzle blindfolded. The revolution came when researchers realized motion could reveal what light could not. Everything within the galaxy moves around the center: stars, gas, clusters, all at speeds dictated by mass. Measure that motion, and you can derive the unseen weight and extent. But something strange emerged. Stars at the outskirts were moving too fast. By visible mass alone, they should have escaped into the void. Something invisible was holding them in place. A vast halo of dark matter, an unseen cocoon of gravity. The earlier surveys failed because they counted only the luminous, the visible stars, the glowing nebulae, and ignored the hidden skeleton keeping it all intact. That was the flaw. Modern instruments overturned everything. The Gaia spacecraft precisely plots the movement of over 1 billion stars. Radio telescopes trace hydrogen clouds that stretch into the outer reaches. Infrared eyes peer through dust, exposing what visible light conceals. Each technology unveils a new layer of the galactic anatomy. Scientists also began tracking the Milky Way's satellite galaxies, the Large and Small Magellanic Clouds, the Sagittarius Dwarf, tiny companions whose orbits reveal our galaxy's total mass, both seen and unseen. Combine all the data, and the answer was staggering. The Milky Way isn't a middling spiral, it's a heavyweight champion, twice the width and thrice the mass of what we believed. And if it's this difficult to measure from within, imagine the challenge farther out. Stellar streams might sound poetic, but they're cosmic evidence, scars of ancient collisions. Long ago, smaller galaxies wandered too close. The Milky Way's tidal force tore them apart, stretching them into luminous trails. Their stars didn't vanish. They flowed into slender rivers wrapping around our galaxy. Some span distances greater than Earth's orbit around the Sun. Others contain thousands of synchronized stars. For years, we ignored them as faint clutter. Yet, they are the galaxy's truest yardsticks. They matter because stellar streams follow the unyielding mathematics of gravity. Every star's movement traces the total mass tugging at it. Follow the river and you follow the gravitational truth, no speculation needed. The Sagittarius stream, the most famous of all, coils multiple times around the Milky Way like a ribbon binding a gift. When astronomers traced its illuminated path, they discovered it stretched far beyond the so-called edge. The stream just continues on and on, telling us that our galaxy's gravity, and therefore its reach, extends far further than we ever imagined. Then came the GD1 stream, a slender ribbon of stars drifting through the galaxy's outer halo. When astronomers traced its arc, they encountered something that defied reason. The path of the stream twisted in ways that demanded more mass than the visible Milky Way could supply. Either our physics was flawed, or something vast and unseen lurked nearby. Dark matter again, the perennial suspect. The stellar streams exposed it as if revealing invisible ink under ultraviolet light. Their curves were sculpted by a gravitational hand we cannot see, a hand stretching twice as far as the bright core of the galaxy itself. Yet what followed was even stranger. Scientists discovered streams looping at distances long believed to be empty intergalactic voids. But the void was not empty at all. These celestial rivers proved that our galaxy's reach extends far beyond what we had imagined. The Milky Way doesn't stop at what we can see. It continues outward, pulling, claiming, dominating. The most haunting of all was the orphan stream. It drifts so far into the darkness that researchers once questioned whether it belonged to us or some distant system. New data resolved the debate. It is ours, and by its presence, the Milky Way's domain stretches that far and beyond. Each new discovery drew the galactic border outward, 5,000 light-years, then 10,000 more, until numbers ballooned, 120,000, 150,000, 180,000 light-years. Stellar streams gave astronomers the most dependable kind of evidence possible, reality itself. You can argue over how far light reaches or where darkness begins, but you cannot argue with the motion of stars orbiting information. Their trajectories told a story that shattered comfort and contradicted tradition. The Milky Way extends roughly 200,000 light-years across. The stars declared it. The mathematics confirmed it. The instruments agreed. The question no longer asked how big the galaxy is, but how we failed to notice for so long. When you gaze at the Milky Way, you believe you're seeing it in full, but in truth, you're only witnessing its skeleton, the luminous framework, not the flesh. 90% of it remains unseen. Dark matter has moved beyond hypothesis. It is quantified, charted, and modeled. We cannot perceive it directly, but its fingerprints are everywhere. Stars whirl too quickly, galaxies spin without tearing apart, and distant light bends subtly around invisible weights. The evidence is insurmountable. In our own galaxy, dark matter doesn't merely add heft. It forms the foundation itself. Imagine a skyscraper where only the windows are visible. The stars are the windows. The dark matter is the steel lattice holding them aloft. Scientists estimate that for every unit of visible mass, there is 10 times more invisible matter, enveloping the galaxy in a diffuse, spherical halo that stretches far past the visible disk. Earlier estimates ignored this hidden structure, focusing on the dazzling spirals and radiant core, mistaking brightness for completeness. The Milky Way was never just 100,000 light-years wide. That was only the part that glowed. The true structure doubles that. Think of it like an iceberg. The shining tip above the surface is what telescopes capture, while a mountainous mass of ice lies concealed below. That unseen mass, the dark matter halo, is the true body of the galaxy. To measure it, researchers use gravitational lensing. When starlight from distant galaxies passes near ours, the dark matter bends it ever so slightly. Measuring that distortion reveals the scale of the invisible. The result was extraordinary. Our halo extends nearly 400,000 light-years when its faint outer edges are counted. But there's a complication. Where does the galaxy actually end? Is it where the halo's density halves? A quarter? A tenth? The transition is gradual, not distinct. There's no edge, just a fading gradient into intergalactic nothingness. For practicality, Astronomers define a virial radius, the boundary where all material remains gravitationally bound to the Milky Way. Inside it, stars and gas orbit collectively. Beyond it, true emptiness begins. Current calculations place this radius between 200,000 and 250,000 light-years, double the once accepted figure, all thanks to the unseen weight of dark matter. This revelation transforms our understanding of galaxies themselves. They're not isolated islands of stars adrift in emptiness. They're vast spheres of dark matter decorated with starlight at their cores. The luminous region is merely detail. The invisible halo is the essence. And if our galaxy possesses such hidden mass, every galaxy must. The universe, it turns out, is far heavier than we ever imagined. The Milky Way does not drift alone. It is surrounded by dozens of lesser companions, satellite galaxies revolving like moons around a planet. The Large Magellanic Cloud, visible from the southern hemisphere as a faint haze, is the largest, containing roughly 30 billion stars. Nearby lies the Small Magellanic Cloud with about 7 billion more. Then come the fainter dwarfs Sagittarius, Draco, Ursa Minor, tiny galaxies with their own star systems, histories, and trajectories. For decades, scientists treated them as transient passers-by. But modern measurements exposed the truth. They are prisoners of our gravity, forever circling within the Milky Way's sphere of dominance. This insight changed everything. By tracking the speed of these satellites, astronomers calculated the immense mass necessary to keep them bound. The faster the orbit, the more massive the host must be. The Large Magellanic Cloud, 160,000 light-years distant, completes an orbit every 1.5 billion years. To maintain such a path, our galaxy must outweigh past estimates by a staggering amount. The same was true for every satellite studied. Each moved faster and farther than predicted. The data left only one conclusion: the Milky Way is both larger and heavier than we'd ever conceived. Tidal streams provided the final confirmation. When a satellite galaxy ventures too near, our gravity tears it apart. Its stars unravel into brilliant ribbons spanning the heavens. The Sagittarius dwarf is currently meeting this fate, its stellar remnants wrapping around the entire galactic sphere. These elongated remnants serve as perfect measuring rods, marking where our gravitational influence peaks, weakens, and ends. When scientists mapped enough of them, the results were astonishing. Streams stretched well beyond the supposed boundary, some 150,000 light-years out, others 200,000, and a few still farther. The satellites and their debris told a single, immutable truth: the Milky Way is enormous. This revelation redrew our local cosmic map. If our galaxy's reach truly extends that far, then the void separating us from Andromeda is smaller, our eventual collision closer in time. Gravitational envelopes overlap, accelerating contact between giants. Every orbiting dwarf became another measurement, each one tracing the invisible bulk of the Milky Way. Together they revealed a leviathan, not a middling spiral. Even more unsettling, some of these satellites orbit at such vast distances we've only just discovered them. Each new one found stretches our border further still. How many remain unseen in the dark? How far does the Milky Way's dominion really reach? 200,000 light-years, perhaps more. The figure defies imagination. Light itself travels at 186,000 miles per second. In a single year, that light covers nearly 6 trillion miles. Multiply that by 200,000. The result, 1.2 billion trillion miles, becomes meaningless to the human mind. Even words collapse under the scale. Suppose you could travel at light speed, our universe's ultimate limit, it would still take 200,000 years to traverse the galaxy's breadth. In that time, entire civilizations could rise, fall, and vanish before light crosses from one end to the other. Think of it this way. If Earth were the size of a grain of sand, the Milky Way would stretch farther than the gap between Earth and Saturn. Farther still, in truth. Or consider this. The light emerging from the galaxy's farthest edge set out long before modern humans, before Neanderthals, even before upright ancestors walked the plains. That light has journeyed since our lineage lived among the trees. Such magnitude obliterates comprehension. The human mind evolved to measure miles, not millions of trillions of them. But this isn't abstraction, it matters now directly. Doubling the galaxy's size means multiplying its volume by 8, since volume scales with the cube of radius. That means 8 times more space, 8 times more stars, 8 times more planets. Earlier estimates listed 200 billion stars. The new figures reach 400 billion or beyond. Each one could host planets, each planet could shelter moons, and some moons could harbor oceans beneath their ice. The number of possible cradles for life has doubled. If existence is rare, say 1 in a billion, then we've just added 200 billion new chances for company. But there's a darker consequence, too. A larger Milky Way means gravitational interactions strengthen, and future events shift closer. The Andromeda galaxy races toward us at nearly 70 miles per second. When galaxies meet, they don't collide like solid worlds. They interweave, passing through each other in vast, silent mergers. Stars glide past untouched, yet the structure of both galaxies transforms forever. But when gravitational turmoil unfolds, it transforms everything. Earlier, astronomers estimated that our collision with Andromeda would begin in about 4.5 billion years. A more massive Milky Way translates to a broader gravitational influence. This means the interplay between us and our neighbor starts even sooner, perhaps in 4 billion years, perhaps less. Should humanity endure that long, your far future descendants will witness the sky's breathtaking transformation. Andromeda, at first a faint smudge, will swell, becoming brighter and finally dominating much of the heavens. Then begins the galactic waltz. Spirals entwining, drawn together, gradually coalescing into a titanic elliptical galaxy. 200,000 light-years is more than a figure. It's your future, your heritage, the arena for every human drama, now revealed to be twice as vast as assumed. Andromeda's approach is no speculation. It's certainty. The neighboring galaxy barrels toward us at 70 miles per second. For years, collision timelines were set around 4.5 billion years from now, based on smaller galactic boundaries and less expansive gravitational fields between these islands of stars. But an enlarged Milky Way pulls harder, bridging the gap ahead of schedule. Gravity's reach extends farther than ever predicted, and the very edges, the immense dark halos of both galaxies, will collide first. Imagine two giants walking toward one another. Their unexpected bulk means they brush shoulders sooner than anticipated. The same applies on this grand scale. New astrophysical projections suggest initial interactions could commence in less than 4 billion years, perhaps nearer to 3.5 billion. While details remain subject to ongoing measurements, the trend is unmistakable. Larger galaxies bring earlier rendezvous. Here's what unfolds during such a cosmic union. First, the furthest reaches, dark matter halos, begin to mingle and blend. Though invisible, these overlapping halos generate profound gravitational effects. Stars across both galaxies start to feel a tug of war, some being hurled outward into the cosmic void, others falling inward toward galactic centers. Soon thereafter, the galaxy's luminous disks intersect. This isn't a violent impact. Instead, it resembles ethereal clouds passing among one another. The vast spaces between stars mean true collisions are vanishingly rare. 1,000,000 Earths could squeeze between neighboring suns. But gravitational tides wreak havoc. Gas clouds compress, birthing waves of new stars. Milky Way and Andromeda will loop around each other repeatedly, spiraling, twisting, clawing at each other's structures. Each dance erodes more of their distinctive shapes. Tidal forces shred spiral arms. Star streams disperse into the darkness. By the end, likely 1 billion years after the first embrace, 2 iconic spirals will have dissolved into a colossal spheroidal galaxy, an elliptical mass of 4 trillion stars racing in random orbits. Astronomers have already given this hypothetical future home a name: Milkomeda, an oddly endearing epitaph for the demise of ancient spiral splendor. Yet the deeper questions persist. Will Earth endure? Will the Sun? Will any living witnesses remain for the show? The optimistic outlook: our Sun's location, safely remote from the core, means it should survive the merge itself, likely avoiding the most intense disruptions. Earth, too, might stay bound, be flung to a new orbit, or get cast into intergalactic emptiness. Most simulations predict survival. But there's a caveat. By then, the Sun will be running out of life. With about 5 billion years left in its fuel tank, the Andromeda event may unfold just as the Sun is nearing its demise. We might glimpse the spectacle's opening acts, but not its finale. And one more twist. What if Andromeda, too, is greater than anticipated? If both galaxies are oversized, then the timeline contracts further and the chaos intensifies. The final supergalaxy would be even more gargantuan. Already, scientists detect the faint outlines of Andromeda's halo stretching toward us, and ours toward them. They may be mingling already, an invisible melding in the dark matter ocean enfolding both galaxies. For billion years may sound boundless, but from a cosmic vantage, it's a heartbeat. That final stitching of the sky is coming a little sooner than we ever guessed. In the end, everything reduces to mass. The Milky Way's recorded weight just surged, an unthinkable bulking up. Trillions upon trillions of solar masses have appeared in the ledgers. Earlier models put us near 1.5 trillion times the mass of the Sun, nearly all of it dark matter, not star or gas. The new calculations: 4 trillion solar masses, perhaps more. In less than 10 years, we've tripled our assessment. To put a solar mass into perspective, our Sun weighs about 2 billion kilograms, a staggering figure. The Earth's mass is a mere fraction, about 300,000 times less. Jupiter is 1,000 times lighter, and every object in the solar system besides the Sun makes up barely 1% of that measurement. Now multiply the Sun's mass by 4 trillion. That's our home, a gravitational behemoth. These extra trillions did not appear overnight. They always existed, their existence masked by invisibility. Most is dark matter beyond vision, only inferred by gravity. Traditional estimates emphasized only what shone: stars, radiant gas. Dark matter was added by inference using galactic rotation curves. Stars whirl at speeds set by total mass. But these methods focused on the inner galaxy, easy to observe, crowded with light. Little consideration was given to the outer halo, where dark matter rules. Here was the oversight. A new era brought fresh methods. The orbital paths of satellites, mapped out farther than ever, served as direct mass benchmarks. Stellar streams charted gravity's grasp in remote galactic territory. Computer modeling compared us to simulations of galaxies with known mass. All agree, 4 trillion times the Sun's heft. The Milky Way is a true heavyweight, and the implications are huge. Greater mass translates to stronger grip. We can hold more satellites, snatch more stars from passing galaxies, extend our influence through the local group. For decades, Andromeda was the dominant sibling, the Alpha Galaxy. But new findings suggest parity, or perhaps the Milky Way is the true giant. Both come in at 4 trillion solar masses, twin powerhouses steering mutual destiny. This added bulk changes our story, too. Galaxies grow by swallowing their neighbors. The more you weigh, the more you have feasted. 4 trillion solar masses mean a bloody heritage, hundreds, perhaps thousands, of smaller galaxies devoured. Each tidal stream in the halo is a relic of conquest, a galaxy that drew too close and was torn apart. Today, the Sagittarius dwarf is being dismantled before our eyes, its stars incorporated into the Milky Way disk. In another few 100 million years, only whispering traces in the data will remain. These are the mechanics of galactic evolution: cosmic cannibalism, relentless expansion. Yet something else is unnerving. If we truly weigh 4 trillion times the Sun, almost all of that is dark matter. We dwell inside a universe composed mainly of the undetectable. 90% of reality slips outside our perception. The galaxy you thought you knew, the safe cosmic address, is mostly illusion. You swim in a sea of shadow you cannot sense, with 4 trillion solar masses of it pressing all around. Galactic borders do not correspond to visible light. The Milky Way stretches endlessly beyond the reach of our telescopes, well into realms mapped only by mathematics and gravitational influence. This sphere, the dark matter halo, is no minor embellishment. It is the scaffolding, the container, the essence. Conservative estimates limit its extent to about 250,000 light-years, the viral radius where the galaxy's pull still binds material. Some models put it at 400,000 light-years, others at 600,000. A few bold calculations push its fringe beyond 1 million. 1 million light-years, 20 times the length cited in textbooks, 20-fold more volume held by gravity's hand. Think of that reach. Andromeda sits just over 2 million light-years away. If both dark halos extend to 1 million light-year radius, a scant 500,000 light-years of emptiness separate us. Our galaxy's halos may already intermingle, two invisible behemoths blending as they prepare for eventual fusion. Despite its enormity, the dark matter halo is elusive. It emits no light, absorbs no radio signals, interacts with nothing except gravity. But that influence is measurable and unmistakable. By following the paths of satellite galaxies, observing how mass bends starlight, and running complex simulations, researchers chart both concentration near the center and the thinning fade toward the edges. There is no edge, only gradual dissolution into the cosmic dark. The halo solves old riddles. Why do the outmost stars race so quickly? The halo's mass tethers them. Why don't galaxies rip apart? Dark matter provides the binding. Why do we witness more gravitational lensing than luminous matter predicts? The halo curves space itself. The most surreal aspect: you are right now within the heart of this vast, unseen field. Every moment you are drenched in dark matter. Invisible particles rush through Earth at hundreds of miles per second. Trillions sweep through your body each instant, streaming straight through, undetected, unimpeded. You remain unaware, untouched by this cosmic flood. Scientists strive to catch direct traces of dark matter, placing experiments deep underground, waiting for the rare event of a collision with a regular atom. So far, the detectors remain silent. The elusive particles refuse to reveal themselves. Too scarce, too delicate, or perhaps we're simply searching in the wrong way. If the Milky Way's dark halo truly stretches 1,000,000 light-years across, our galaxy dominates an immense volume of space. Most of the local group lies quietly within our gravitational authority. We aren't merely a galaxy. We are an empire of gravity, a colossal superstructure of unseen mass exerting quiet dominion over everything near us. And if our halo expands that far, every other galaxy possesses one as well. The universe isn't a scattering of isolated islands glowing in void. It's a vast ocean of overlapping halos, with galaxies nestled like bright seeds within invisible fruit. Nearly all of existence hides in shadow. The luminous universe is mere decoration upon an unseen framework. 1,000,000 light-years of darkness, that is the Milky Way. That is our home. And only now are we beginning to grasp how truly immense it is. Yet something about our galaxy's motion refuses to make sense. The entire Milky Way spins too quickly. It should have torn itself apart long ago. Stars on its outskirts orbit at impossible speeds, their trajectories violating classical expectations. They should have escaped into intergalactic space. They should obey Kepler's ancient laws, slowing as they move farther from the center, but they don't. Here lies the enigma. In our solar system, orbital speed diminishes with distance. Mercury races around the Sun in just 88 days. Earth takes a year, Neptune 165 years. The farther the planet, the weaker the gravitational pull, the slower the motion. Perfectly logical, precisely as Newton calculated centuries ago. Logically, galaxies should behave the same way. Stars farther from the center should orbit more languidly. Instead, when astronomers map the speeds, the expected downward slope refuses to appear. The curve remains flat. This should be impossible, unless some hidden mass lurks beyond what we can see. Always dark matter. Only that invisible halo can provide the additional pull needed to keep distant stars moving fast. The Milky Way's flat rotation curve stands as the undeniable fingerprint of dark matter's presence. Yet even after accounting for it, the puzzle deepens. Measurements reveal motions even faster than predicted. Some outer stars hurtle at 130 miles per second, others at 150 velocities, brushing the threshold of escape. They skirt freedom but stay confined, balanced at the edge of flight. What delicate mechanism sustains that equilibrium? Astronomers call it the escape velocity problem, a haunting question. Perhaps our estimates still fall short. The dark halo may be denser at great distances than expected. Maybe our mass counts remain too small. Or the explanation could be recent growth. If, in the past few billion years, the Milky Way consumed a sizable dwarf galaxy, the merger could have scattered an influx of stars into rapid, unsettled orbits. Evidence supports this idea. As we speak, the Sagittarius dwarf is being devoured. Its stars, flung outward, disperse across the galactic halo at extraordinary speed. In another billion years, they'll blend seamlessly into the background population of swift, barely tethered stars. But even that's not the end of the mystery. Some stars move too slowly, the mirror image of hypervelocity stars. They linger sluggishly, orbiting well below expected speeds, as though trapped in cosmic molasses. No model explains them cleanly. The rotation curve should be straightforward. Measure speeds, deduce mass, match the prediction. Instead, every new observation brings exceptions, anomalies, deviations that shouldn't exist. This is where theories of dark matter are tested to their limits. Different models yield distinct rotation behaviors. Warm dark matter leads to smoother curves. Cold dark matter generates clumpier distributions. self-interacting dark matter changes flow patterns within galactic centers. So far, evidence favors the cold model, though not perfectly. Discrepancies persist, minute but persistent, the kinds of deviations that hint at undiscovered physics or perhaps at the limits of our measurement tools. The Milky Way spins harder, faster, stranger than it should. The larger its newly measured size, the deeper this contradiction becomes. More stars, more volume, more odd trajectories awaiting explanation. Everywhere else in the cosmos, from star clusters to faraway galaxies, gravity behaves predictably. But right here, in our cosmic backyard, something still refuses to add up. Even our blueprint of the Milky Way's structure is under debate. Once, we were certain it had 4 great spiral arms: Scutum, Centaurus, Norma, Sagittarius, and Perseus, each a luminous highway of gas, dust, and newborn stars unfurling from the core. But certainty is short-lived. Improved instruments changed the picture. Infrared telescopes pierced the dust, radio arrays traced hydrogen gas, and space-based observatories offered clarity untouched by atmosphere. With each advance, hidden patterns emerged. An unexpected, far 3 kiloparsec arm appeared first, a massive spiral limb concealed behind the galactic center, invisible to optical eyes but clear in infrared maps. Then astronomers noticed the so-called local arm, home to our own solar system, might not be a minor spur after all. Some data suggest it connects seamlessly to broader structures, making it a true arm in its own right. Even the outermost fringes, once dismissed as scattered star clouds, revealed coherent spirals extending well past visible boundaries. The galaxy shows design where we once assumed emptiness. And yet, the mechanism behind those spirals remains an unsolved riddle. Nearly every disk galaxy flaunts them, these graceful, symmetrical curves of light, but the physics that sustains them defies expectation. The issue lies in orbital speed. Stars closer to the center rotate faster than those far out. If spiral arms were composed of fixed groups of stars, differential motion would twist them tighter and tighter, smearing them into an indistinct blur after only a few revolutions. But that never happens. Spiral arms persist for billions of years. Thus was born the density wave theory. The notion that spiral arms are not permanent structures but moving patterns, regions where stars momentarily cluster, giving the illusion of form. The analogy is traffic on a highway. Cars bunch up, forming a slow-moving wave, yet individual vehicles keep passing through. The pattern persists even as its participants change. The mathematics works beautifully, but then reality complicates it. Some arms display too many young stars. Others have yawning gaps where density should peak. The Milky Way's outer arm appears too massive, too coherent, to be explained by waves alone. It could be the remnant of a collision, a scar left by a galactic feast. The galaxy's expanded scale complicates all of this further. Greater area means new territory for complexity. Room for extra arms, overlapping waves, unforeseen features. Data from the Gaia spacecraft, tracking over 1 billion stars with exquisite precision, revealed branching substructures within known arms. Offshoots, gaps, clusters, scattered trails. The Milky Way's design emerges less like a textbook spiral and more like an intricate tangle of light, chaotic, organic, alive. Some scientists now argue it isn't a grand design spiral at all but a flocculent galaxy, where spiral arms twist and fade irregularly. This would explain why each survey sees a slightly different form. Every instrument, tuned to different gases or wavelengths, reveals another version of home. The debate rages on: more telescopes, more data, more midnight arguments at astronomical conferences, but consensus grows on a single truth. The Milky Way is far more complicated than any elegant four-arm diagram once suggested. Across its disk lie hidden arms we failed to notice for decades, and their discovery forces a painful question. If we overlooked entire limbs of our own galaxy, what else have we missed? What other marvels linger unseen, waiting for the right lens, the right wavelength, the right human curiosity? Even the act of defining our galaxy's boundary proves elusive. Draw a line, they say, to mark its edge. But the cosmos refuses simplicity. Galaxies don't end cleanly, with borders or signs declaring, "Now leaving the Milky Way." Their stars simply fade, dimmer and rarer, until they vanish into the night. So where does our dominion truly stop? The dilemma is not philosophical, it's practical. Astronomers need agreed definitions, consistent ways to compare galaxies. The universe, indifferent to categorization, provides none. Several methods compete, each imperfect. The optical radius measures where visible stars drop below detection. That gives us the bright disk, around 100,000 light-years wide, but it ignores the faint outskirts, the dim dwarfs, the ancient halo. It's like gauging the size of a city by counting skyscrapers and ignoring its endless neighborhoods. A better measure is the virial radius, the boundary where objects remain gravitationally bound to the galactic core. Inside, everything orbits together. Beyond, motion drifts away into independence. For the Milky Way, that radius lies around 250,000 light-years, an improvement though still not flawless. Some stars beyond that boundary continue moving with the whole galaxy, sharing its drift through the cosmic sea. Were those stars born here? Do they still belong to us? According to the virial radius, no. According to intuition, maybe. Beyond even that lies the dark matter halo, stretching far past every visible boundary. If it truly extends 1,000,000 light-years, could that be the real edge? Most astronomers would say not. The halo tapers away so gently that any chosen border is arbitrary, like trying to decide where Earth's atmosphere ends. Technically, it stretches thousands of miles outward. Practically, it fades after a mere 100. Where, then, do we set the line? The problem deepens when we consider galactic winds. The Milky Way breathes. Massive exhalations of gas and energy flow outward through its halo. Supernovae burst, stars shed layers of themselves, and that material streams into the void, traveling hundreds of thousands of light-years beyond the disk. Is that still our galaxy's gas? Or the intergalactic mediums? Some of it rains back down, pulled home by gravity. Some drifts away forever, lost to the cosmic gulf. At what point does ownership end? The Magellanic Stream complicates things further. As the large and small Magellanic Clouds orbit, they leak gas, leaving a ribbon of hydrogen stretching across the heavens. Does that thread belong to them, to us, or to neither? Each claim has its defenders, and all are right in their own way. Andromeda faces the same paradox from its side. If its dark matter halo already overlaps ours, what border can we meaningfully draw? The shared space between becomes contested territory, a cosmic no man's land held by both. This isn't mere semantics. The chosen definition changes everything: our estimates of mass, our assessment of size, even our timing of Andromeda's approach. If the halos are already merging, the great collision has already begun. We are living inside the opening act. Most astronomers adopt practical conventions. The stellar disk ends where star formation ceases. The halo extends out to the virial radius. The dark matter halo continues as far as simulations require. Each definition serves a purpose. None tells the whole truth. In reality, the Milky Way is not a single object. It's a region, a gravitational domain with a dense heart, a structured body, and a diffuse periphery that dissolves into the universal sea beyond. For now, 200,000 light-years remain our best estimate. But ask again in a decade, and the answer will change as it always does. The universe resists edges. It bleeds and blends. Nothing truly ends. Everything connects. We occupy a cosmos with no borders, and we are only just learning how to measure it. At the galactic frontier, stars race at near impossible speeds, 130 miles per second, 150, even up to 200. They should have broken free, yet they remain tethered. These are high-velocity halo stars, moving just below the threshold needed to escape. Barely bound, skating along the edge of freedom. Detecting them proved an immense challenge. They are faint and sparsely scattered across unimaginable distances. But surveys like Gaia's have mapped their motion with exquisite precision. One discovery stands out. A star in the outer halo traveling at 198 miles per second, with the local escape velocity estimated at 200. A mere 2 mile per second difference separates confinement from eternal flight. It's the astrophysical equivalent of a rocket clinging to Earth's pull by a thread. Why do so many trail the same precarious line? It's not coincidence. Something set them there, gifted them that exact measure of energy and no more. Galactic consumption offers one explanation. Each time the Milky Way swallowed a smaller companion, the collision injected waves of kinetic energy. Stars hurled from the wreckage settled into fast, unstable orbits. The Sagittarius dwarf, currently being devoured, shows this process in motion. Its stars strewn across the halo, scattered like sparks from a dying ember. 1 billion years from now, they'll blend seamlessly with the rest, indistinguishable except in memory. Another process may be at work: three-body interactions. When two stars encounter a third companion, gravity can slingshot one outward while the others recoil. Such events occur in dense clusters, occasionally launching one star clear into the galactic halo. Most flee entirely. Some land on that razor's edge, fast but not free. Nearby black holes introduce another twist. A close pass near a massive black hole can accelerate a star to tremendous speed, either flinging it to the outskirts or out into the intergalactic void. At the Milky Way's center, a black hole 4 million times more massive than the Sun serves as the ultimate slingshot. Some stars that strayed too close have been ejected at more than 400 miles per second. True hypervelocity stars, speeding beyond recovery. Their paths trace back to the core, suggesting binary interactions in which one partner was captured and the other expelled. But for the nearly bound stars lingering at the edge, the story must differ. They aren't escaping the core. They were born or thrown into the halo long ago, moving swiftly yet steadily along its invisible rim. A provocative theory suggests that the dark matter halo itself holds the key. If its distribution is not smooth but clumpy, gravitational concentrations could create stable high-speed orbits, zones where stars remain locked at near-escape velocity. In this model, those fast-moving halo stars are test particles tracing the contours of dark matter's invisible sculpting. But proving it is an enormous challenge. We cannot see dark matter directly, only infer its arrangement through stellar motion. If the halo truly contains lumps, astronomers should observe clusters of high-velocity stars grouped together in resonance. Some surveys hint at these gatherings. Others show chaos instead. The data remains ambiguous. What's certain is that the galaxy's outskirts defy expectation. The line between bound and unbound is razor thin, just a few miles per second separating loyalty from abandonment. As the Milky Way's boundaries expand, more stars linger in this unstable zone, balanced between home and eternity. Understanding why reveals the deeper architecture of galaxies, the nature of dark matter, and the subtleties of gravity itself at interstellar scales. The Milky Way's conundrums ripple beyond our own sky. If our measurements were wrong here, they're likely wrong everywhere. This chilling possibility keeps astronomers awake at night, running and rerunning the numbers. If every galaxy is larger than recorded, perhaps twice as large, the cosmic census needs to be rewritten from the ground up. That revelation has sweeping consequences. Astronomers derive their understanding of the universe from galaxies. Their distribution, their mass, their role in the cosmic web, their influence on the expansion of space. Increase their size, and the entire framework shifts. Bigger galaxies have stronger gravity. They capture more neighbors, strip more stars, shape clusters in new ways. Recalculate the masses, and you must rebuild the history of galactic evolution itself. Even cosmology trembles at the implications. Distance measurements depend on standard candles, galaxies of known brightness used to gauge cosmic scale. But if those galaxies are more massive, they shine differently. Their luminosity changes, so their inferred distances change. If the distances shift, so too does our measurement of cosmic expansion, and with it, the strength of dark energy. The smallest error ripples across every equation describing the universe. Scientists are now double-checking the great surveys, the Sloan Digital Sky Survey, the 2-micron All-Sky Survey, and countless others, using new techniques that factor in stellar streams and satellite galaxies to refine galactic size. The results are unsettling. Many galaxies appear far larger than cataloged, some by half, others by double. The pattern is consistent. We have systemically underestimated. Andromeda, larger. Triangulum, larger. Every major galaxy in the local group demands revision. If nearby ones are bigger, then distant ones likely are too. The cosmic web tightens. Space grows denser, gravity stronger. Bigger galaxies contain more dark matter, skewing the ratio of seen to unseen material. That rebalances every theory on galaxy formation and cosmic evolution. It even resolves some long-standing puzzles. Take the missing satellites problem. Simulations predict hundreds of satellite galaxies orbiting each major system, but we find only dozens. If halos stretch farther, the missing companions may simply orbit too far to see. Or consider rotation curves, the very puzzle that birthed the dark matter concept. Many galaxies exhibit the same flat pattern. Extending the halos outward brings the models closer to observed behavior. Yet with each correction, new complications arise. Larger galaxies mean less space between them. The universe grows crowded. Interactions become inevitable. Mergers happen sooner, the chronology of cosmic history compresses. Galaxy clusters, huge gravitational collectives, must be reconsidered as well. If each member galaxy exerts a wider pull, the cluster's overall dynamics change. Mass distributions must be recalculated, dark matter reweighed, simulations adjusted. Even the early universe feels the shock. If galaxies forming billions of years ago were bigger, structure emerged faster, maturity arrived early, and cosmic history accelerates. The repercussions cascade through stellar evolution, black hole growth, the behavior of dark energy, everything we thought we'd understood. We are rewriting the universe itself, reevaluating every galaxy, every cluster, every piece of the cosmic web. The emerging cosmos is vaster, denser, and infinitely more intricate than the one we once pictured. The Milky Way was only the first revelation, the initial domino whose fall now topples everything else. Yet even here, in our home galaxy, another surprise lurks. The Milky Way spins around a single point, not the supermassive black hole, not the bright core, but the true center of mass. And it's not where we thought it was. The concept sounds simple, the balance point where all mass, visible and hidden, evens out. For a ruler, that's its midpoint. For Earth and Moon, it's a spot inside Earth but off-center, pulled slightly toward the Moon. For the galaxy, it's the point about which everything rotates. Astronomers long assumed that point lay precisely at the visible core, the black hole's lair, logical enough since light and stars cluster there. But they neglected the influence of dark matter. Unlike luminous matter, dark matter doesn't sit in the middle. It surrounds everything in an enormous, uneven halo, thicker here, thinner there. This asymmetry shifts the balance point slightly, enough to matter. Recent recalculations, incorporating the Milky Way's expanded mass and revised halo structure, moved the center of mass away from the visible core, not by thousands of light years, but far enough to reshape our models. A few hundred light years, perhaps 1,000. To astronomers, that sounds trivial. In human terms, it's staggering. The galaxy's balance point has shifted by a span greater than the distance from Earth to our nearest star, wider than dozens of solar systems lined up one after another. Why does that matter? Because everything orbits the true center of mass, not the spot of brightest light. Every star's motion, every satellite's path, depends on that hidden equilibrium point's position. Determining it isn't easy. It requires knowing the velocity of stars scattered across the entire Milky Way, mapping dark matter distribution in 3 dimensions, and simulating the total gravitational field with painstaking accuracy. Only in the last few years have our instruments grown capable of teasing out this discrepancy. The Gaia spacecraft provided the breakthrough, tracking positions and motions for more than 1 billion stars with astonishing precision. Feeding that torrent of data into supercomputer models, scientists reconstructed the complete gravitational map, and what they found defied assumptions. The Milky Way's center of mass does not align precisely with its supermassive black hole. The shift, slight but real, changes how we understand our cosmic motion. The solar system takes roughly 230 million years to complete one revolution, a galactic year. Even a small offset means our orbit is subtly faster or slower than thought. These differences ripple through every model, complicating the elegant symmetry astronomers once used to describe the galaxy. Real galaxies are not perfectly balanced systems. They're scars of ancient collisions. Each merger with a smaller companion left a gravitational bruise, displacing mass, bending symmetry. The Sagittarius dwarf, currently plunging into our disk, alone exerts measurable influence. Minor on the galactic scale, but persistent, each swallowed neighbor nudges the Milky Way's balance point a little. Some scientists believe the center of mass oscillates over time, shifting like a pendulum as fresh galaxies fall in and dissolve. The Milky Way, far from still, is alive, devouring, evolving, changing its center with every cosmic meal. Here's the strangest question born of that realization. If the center of mass sits offset from the black hole, what does that imply for the black hole itself? These monsters are expected to reside at their galaxy's exact hearts, anchored by the gravitational symmetry that nurtured them. But what if the balance point no longer coincides? One answer is temporal. The black hole formed long ago, when the Milky Way was smaller and structurally even. Mergers altered the galaxy's distribution of matter, pushing the equilibrium elsewhere, But the black hole, 4 million solar masses of inertia, stayed put. Nothing short of another supermassive collision could easily move it. Another solution sees this as a phase, a transient imbalance that will resolve itself in cosmic time. As the galaxy relaxes, symmetry may slowly return, drawing the center of mass back toward the core. For now, however, the 2 points are divided. Our galaxy spins around a spot that is not where we once believed, a subtle displacement, tiny by cosmic measure, enormous by human scale. And we are only beginning to grasp its consequences. When galaxies collide, the images are deceptive. There's no roaring explosion, no violent smash, just a grand gravitational ballet performed at 1 frame per million years. But scale transforms everything. Large galaxies don't merge like small ones. The same physics plays out on a vastly different stage, producing more elaborate and enduring choreography. For small galaxies, the collision is brief, hundreds of millions of years. 2 objects meet, merge, and stabilize. But when giants like the Milky Way and Andromeda embrace, the performance stretches across billions. Greater mass strengthens gravity. Stronger gravity complicates every interaction. Here's how such a colossal merger unfolds. First contact happens invisibly, when their immense dark matter halos overlap. Long before any visible stars meet, gravity has already started weaving the 2 giants together. The halos interpenetrate effortlessly, like ghosts passing through one another, yet their gravitational fingerprints distort orbits across thousands of light years. Stars at the outskirts feel dual pulls. Their paths warp. Chaos begins. Next, the outermost regions, stellar halos rich with high-velocity wanderers, collide. Some of those barely bound stars gain enough energy to break free, flung into dark intergalactic exile. Others are captured by the oncoming galaxy, ripped from one and absorbed by the other. The galaxies begin swapping stars like traders exchanging relics. Then the tides rise. Gravitational forces tug more strongly on one side than the other, stretching both galaxies until threads of stars and gas tear free in luminous streamers, tidal tails, arcing millions of light years into emptiness. Each tail a banner of destruction, a trace of 2 spirals locked in combat. Finally, the visible disks intersect. No impact, no detonation, just interstellar clouds colliding, compressing, condensing. Gas collapses, pressure builds. New stars ignite by the millions in vast stellar nurseries. Entire galaxies flare brighter as star formation surges in a brief, feverish burst. Astronomers call such systems starburst galaxies, cosmic fireworks born from collision. But size dictates survivability. Large galaxies possess deep gravitational wells. Materials stretched into tidal tails will often fall back, drawn home again. Smaller ones lose their material forever. The Milky Way and Andromeda will shed stars, but most will return, their gravity too strong to allow complete escape. Mergers of this scale drag on. Rather than blending after 1 or 2 passes, the galaxies will loop around each other repeatedly 3, perhaps 4 or 5 times. Each orbit robs momentum from their motion, tightening the spiral until their cores finally meet. Gas friction, stellar encounters, and gravity together bleed away energy. When it ends, the 2 once grand spirals will dissolve into a single luminous oval, a giant elliptical galaxy. No more arms, no organizing disk, only a chaotic field of stars whirling without order. Astronomers have already named this future titan Milkomeda, the merged legacy of 2 kindred spirals. It will be vast, roughly 800 billion stars, 4 trillion solar masses, a heavyweight in the local group. Deep within its merged heart, the Milky Way's 4 million solar mass black hole will collide with Andromeda's billion solar mass monster. Their union will unleash titanic gravitational waves rippling across the cosmos. Disturbances so intense they'll be felt billions of light years away. The merger will spark immense beauty, but also decline. The starburst phase burns through remaining gas quickly. Within a few billion years, little fuel remains. Star birth ceases. The glowing spiral arms fade. Milkomeda will become a quiescent, reddish giant, ancient, massive, and silent. Large galaxies merge slowly, but they merge spectacularly, prolonged, intricate, and transformative. And we are witnessing the prelude. The first hints of contact may have already begun. The silent mingling of our halos could be underway at this very moment. The collision of galaxies is not a future event. It's a present process, unfolding invisibly before our eyes. And as this drama plays out, new mysteries surface. There is still mass unaccounted for, matter predicted but unseen. Astronomers call this the missing mass problem, and recent data has made it several times worse. Here's the challenge. Sum every visible piece of the Milky Way, stars, dust, planets, gas, and you get roughly 200 billion solar masses. Measure total gravitational pull, however, and you find about 4 trillion. The discrepancy is explained by dark matter, an invisible ocean binding us together. But even when dark matter is factored in, something still doesn't add up. By simulation, galaxies should contain a specific ratio of normal, baryonic, matter to dark matter, ordinary protons, neutrons, the tangible stuff of existence. In practice, we fall short. Only about half the expected baryons are visible. The rest have vanished into hiding. Where did they go? 3 leading theories compete. The first, expulsion. Over time, violent events, supernovae, stellar winds, or energy from active black holes blow enormous quantities of gas outward. This matter isn't gone. It lies diffuse and faint among the galactic outskirts, stretched thin across intergalactic space, too cool and sparse for our instruments to detect. The second, concealment. The missing baryons might exist as invisible reservoirs, frigid gas clouds too dim to see, swarms of brown dwarfs too faint to measure, or rogue planets adrift between stars. Hidden, not gone, beyond present detection. And the third theory, the most unsettling, perhaps the missing matter never entered the galaxy at all. The intergalactic medium, the vast emptiness between galaxies, contains ultra-thin gas spread over millions of light years. It could be that much of our galaxy's missing mass was never captured, floating forever in the spaces between worlds. But stretched across such immense distances, even the thinnest gas accumulates. Over cosmic volumes, it adds up. Perhaps half of all baryonic matter in the universe drifts within this diffuse intergalactic medium, never captured by galaxies at all. Recent evidence favors the first theory. X-ray observatories have detected enormous halos of superheated gas surrounding galaxies. Too hot to condense into stars, too sparse to see easily, yet undeniably present. This gas exists in a strange middle state, ionized, energetic, invisible to most wavelengths, but substantial. When astronomers measured these halos, they discovered vast stores of mass, enough to explain much of the missing material. For a moment, it seemed the puzzle was solved. But then came the revelation that the Milky Way is larger than we thought, and the balance broke again. A galaxy weighing 4 trillion suns should, by cosmic standards, contain about 400 billion solar masses of ordinary matter. Yet we can only account for roughly half seen as stars, gas, dust, planets. The rest has vanished into shadow. Tripling the Milky Way's mass triples the scope of its missing matter. Where did hundreds of billions of solar masses of baryons go? Logic says they must dwell somewhere, within the halo, the disk, the interstellar medium, but our instruments find only absence. Some astrophysicists suspect the dark matter halo hides vast caches of hot gas, trapped hundreds of thousands of light years from the center. The gas may be so scalding, so rarefied, that current X-ray telescopes can barely detect its faint glow. It might contain enormous masses right under our noses, invisible but real. Future observatories, built to sense the softest X-rays, could finally uncover these hidden reservoirs, oceans of baryons waiting in the darkness. Others turn their eyes to the circumgalactic medium, the vast transition zone ringing the galaxy where matter endlessly cycles in and out. Supernovae and stellar winds hurl material outward, where it cools, condenses, and falls back again, replenishing star-forming gas in an eternal loop. This cosmic breathing creates a cloud of baryons neither truly inside nor outside, a liminal mirror of the galaxy itself. The James Webb Space Telescope, with its exquisite infrared vision, is now hunting these evasive atoms, searching for their warm, spectral signatures. Early findings hint that the Milky Way's outer halo may contain far more matter than previous surveys recognized. But like every frontier in astronomy, the answer awaits more eyes, more data, more time. And that is the disquieting truth. We dwell within a galaxy where half the ordinary matter remains uncounted. We map dark matter with relative confidence. It's the luminous matter that hides from us. Each increase in galactic mass multiplies the unknown. The bigger the Milky Way gets, the larger its mystery grows. Somewhere in that immensity, 400 billion solar masses of ordinary substance are waiting to be found. And yet again, we remind ourselves the Milky Way is not exceptional. That lesson surfaces everywhere in astronomy. Each time we believe ourselves unique, the cosmos reminds us we are not. The same mismeasurements plague every spiral galaxy, near and far. To test this, researchers re-examined their nearest neighbors, Andromeda, Triangulum, and several smaller spirals, applying the same modern techniques: satellite tracking, stellar stream mapping, and refined models of dark matter distribution. The result was universal. Every single galaxy came back bigger, some by half, others nearly doubled. Andromeda's diameter, once placed at 220,000 light-years, now stretches beyond 300,000 and perhaps further, its dark matter halo sprawling well beyond what old metrics allowed. Triangulum expanded too, from 60,000 light-years to nearly 100,000. Even galaxies cataloged by number NGC 524, NGC 2976, and dozens like them all grew under scrutiny. The pattern was clear, systemic, and staggering. We had been measuring galaxies wrong for decades. The error stemmed from light itself. Old surveys stopped where starlight faded from view, mistaking visibility for existence. They mapped the dazzling cores but ignored the faint outskirts. They measured the bright disks and forgot the ghostly halos. Modern tools, sharper and deeper, transformed that vision. Wide-field telescopes now trace galaxies edge to edge. Infrared sensors pierce the dust. Deep exposures reveal whisper-thin rings of stars at the rims, and satellite orbits, nature's own gravimeters, expose the full mass each galaxy commands. Other spirals follow the same template as ours. Like the Milky Way, they possess flocks of satellites, tiny companions orbiting unseen. Track those satellites, measure their speeds, and the true scale emerges. Andromeda alone has dozens, their orbits betraying a gravitational footprint far larger than any visible halo suggested. Stellar streams crisscross its outskirts, shimmering trails from devoured galaxies looping far past the luminous disk. These too testify to Andromeda's size, its reach, and its hunger. When astronomers factored in the full extent of dark matter halos, spirals became titans. Their gravitational empires stretch hundreds of thousands of light-years, their influence eclipsing the empty sky between them. The space between galaxies shrank. Suddenly, the universe appeared tighter, more crowded, alive with constant gravitational friction. Collisions once thought rare began to seem inevitable, ongoing, ubiquitous. The consequence cascades outward. If galaxies are larger, their halos overlap more frequently, accelerating interactions. The universe becomes more violent, its web of structure denser and more dynamic than imagined. The number of galaxies within a fixed cosmic volume also changes. Fewer fit within the same space once each radius expands. That shift rewrites cosmological models, alters predictions for how clusters evolve, and reshapes our understanding of cosmic architecture itself. Even rotation curves, the puzzle that birthed dark matter, start to fall neatly into place. The flat orbital speeds observed across so many spirals finally make sense when the galaxy's full breadth and hidden mass are acknowledged. The physics works almost perfectly. This trend doesn't stop with the giants. Dwarf galaxies, too, appear larger than once thought, their faint halos stretching quietly beyond visibility. The error is universal, spanning every scale. Elliptical galaxies, though harder to define without distinct arms, also show signs of enlargement. Everywhere astronomers look, galaxies grow. The conclusion is unavoidable. For decades, humanity has drawn its galactic maps too small. We counted only what glittered and overlooked the vastness that glowed too faintly to see. Every spiral galaxy in the universe, ours included, is markedly larger than textbooks declare. The cosmic census must start anew. We live in a grander, denser universe than we ever believed. And that revelation tightens everything close to home. The local group, the Milky Way's neighborhood, hasn't expanded. Rather, its internal boundaries have melted together. What seemed open space between galaxies now lies under overlapping reigns of gravity. The Milky Way, Andromeda, Triangulum, three giants, each surrounded by retinues of dwarfs, command this region of space. We once estimated about 80 galaxies inside a 10-million light-year sphere. But the borders were drawn when our scales were flawed. Now, those gravitational borders stretch wider. Territory once thought intergalactic now belongs to someone. It's either ours or theirs. The no man's land between giants narrows dramatically. The old map placed 2.5 million light-years between the visible disks of the Milky Way and Andromeda. But both halos extend roughly 250,000 light-years outward, perhaps more. Subtract those shells, and only about 2 million light-years of free space remain. Less if the halos overlap. Some models already suggest they do. If that's true, the collision of our galaxies has already begun, imperceptibly slow but inexorable. The local group is no longer three sovereign entities separated by emptiness. It's a tangle of overlapping gravitational spheres, a federation of influences fading into one another. Even our satellites are caught in this slow-motion convergence. Take the Magellanic Clouds. Once thought temporary visitors, their fates are now sealed. With the Milky Way's newly measured gravity, they are trapped, bound to spiral inward, fated for assimilation. Other dwarfs drift in neutral space between us and Andromeda, uncertain citizens of both realms, tugged by two masters. Over the next few billion years, these fragile worlds will tear apart, scattered by the compounding pull of giants. Triangulum stands on that same precarious threshold. The smallest of the three great spirals, home to 60 billion stars, is now likely tethered to Andromeda itself. Their halos nearly touch already, the distance between them a mere 750,000 light-years. Triangulum may no longer be an equal, it's a satellite awaiting absorption. Redefining these borders reshapes our cosmic census. Some galaxies once deemed independent turn out to be captives. Others once labeled as satellites have slipped free. The total remains roughly constant, perhaps 80 members still, but the relationships, the hierarchy, the balance of power all change. And even the central balance of the local group shifts with it. As every galaxy grows heavier, their combined center of mass slides subtly across the dark, unseen space that binds them all. With the recalibration of galaxy sizes and masses, the very balance of our cosmic neighborhood shifts. The gravitational center of the local group moves, now resting somewhere between the Milky Way and Andromeda, though still leaning closer to Andromeda, since it may outweigh us by a narrow margin. This invisible point governs everything around it. Every orbit within the group, dwarfs, satellites, and even the great spirals themselves, bows to its pull. The entire system turns upon this balance point. Farther out, the boundaries between neighboring clusters must be redrawn. 2. The Sculptor group lies roughly 12 million light-years away. The Maffei group hides closer still, shrouded behind the Milky Way's dense disk. Each cluster maintains its own gravitational dominion, but as galaxies grow, those domains swell, shrinking the void between them. Some astronomers now suspect the local group itself stretches farther than we ever allowed. 15 million light-years across, not 10. Its outer members wander more distant paths, yet remain tethered by gravity's reach. The group now occupies more space, claims more mass, and exerts control across a grander volume of cosmic structure. This redefinition ripples upward through the hierarchy of the universe. Small groups form superclusters, and ours belongs to the Virgo supercluster, or perhaps to the even larger Laniakea complex, depending on where one draws the lines. But if groups are larger, superclusters must be reimagined. The entire architecture of structure formation must adapt. Here lies the irony. Boundaries themselves are illusions. Galaxies do not obey human cartography. They blur, entwine, and merge. The universe does not recognize fences or borders, only smooth gradients of matter and force. What we call galaxies are eddies of higher density within a seamless ocean of gravity. The local group isn't a neat cluster of isolated islands. It's one enormous gravitational basin, filled with swirling concentrations we label as independent worlds. Redraw the lines however you like. The cosmos refuses to be boxed in, and we, adrift inside it, are simply trying to chart chaos that resists every map. Within that basin, the numbers grow dizzying. The Milky Way alone now hosts roughly 400 billion stars or more. Every estimate doubled alongside its size. For 100 billion, the number defies comprehension. If you counted one star per second, it would take over 12,000 years to reach the total, longer than all of recorded human history. Even then, you'd have billions left uncounted. For perspective, Earth holds 8 billion humans. You'd need 50 Earths, each fully populated, to match the number of stars flickering in this galaxy. Old estimates capped the total at 200 billion, but those relied on flawed sampling. Astronomers once counted stars in the regions near the Sun, then extrapolated across what they believed to be the galaxy's size. But doubling the galactic radius multiplies volume by 8. Even sparsely populated regions add up. Most of the added mass resides in the faint outer disk and halo, regions previously invisible. They are dominated by red dwarfs, tiny and dim but abundant beyond measure. These small suns, making up roughly 70% of all stars, contribute little light but immense numbers. New instruments sensitive to faint infrared signals now uncover them. Hundreds of millions of ancient, metal-poor stars orbiting at the limits of our halo. Many are relics from the galaxy's youth. Others are the orphans of cannibalism. Every time the Milky Way absorbed a smaller neighbor, it inherited that galaxy's long-dead stars. Their remains drift among ours now, former citizens of conquered realms. The Sagittarius dwarf alone surrendered roughly 100 million stars during its slow disassembly, wrapping around us as a luminous scar. All of them have joined our census. 400 billion stars means 400 billion chances for planets. Not every star hosts one, but most probably do. Observations suggest at least 60% of stars have planetary companions, meaning more than 240 billion worlds orbit within our galaxy. Of these, perhaps 1% lies in the narrow temperate zones where liquid water could exist. That's 2.4 billion potentially habitable planets, twice as many as once believed. Even if only 1 in a million nurtures life, we're left with thousands of living worlds scattered through the Milky Way. And if intelligence is rare, say 1 in a billion worlds achieving thought, that still leaves 2 or 3 civilizations besides our own. The parameters in the Drake equation all just grew. More stars, more planets, more opportunities. The probability of alien life just doubled. It remains uncertain, but the needle of chance moves closer to hope. And yet, the silence persists. 400 billion stars, billions of planets, and not one confirmed signal. Where is everyone? Why haven't we heard from anyone else? The Fermi paradox grows sharper with every upward revision of these numbers. Perhaps a great filter stands in the way, a cosmic barrier culling civilizations before they spread to the stars. Maybe that filter lies behind us, and life itself is the improbable step we somehow cleared. Or perhaps it lies ahead in self-destruction, nuclear fire, ecological collapse, or technology turning on its creators. Some suggest that intelligence is even rarer than we believe, and that maybe we are, for all practical purposes, the only one. Imagine that, for 100 billion suns, one small planet whispering into a silent void. And yet, optimism flickers. A galaxy twice as large means twice as many chances for conversation. For every sun, a potential neighbor. For every planet, another opportunity. SETI, the search for extraterrestrial intelligence, becomes both more daunting and more promising. Twice the search space, but twice the possible callers. Future observatories may look for indirect clues. Biosignatures, oxygen, methane, ozone, in alien atmospheres. The James Webb Space Telescope is already leading the hunt. With every newly discovered Earth-like world, the equation tilts a little further toward the possibility that we are not alone. The odds have improved. The hope feels justified. Somewhere in this widened galaxy, another form of life may be asking the same question, watching the same stars, waiting for an answer that has not yet come. The Milky Way's expansion doesn't just enlarge our map. It expands our sense of wonder. Stand now at the edge of the galaxy and peer outward. Where exactly does it end? The answer is unsettling. Nowhere. There is no boundary, no cliff into intergalactic space. The galaxy fades gradually, like air thinning at the top of Earth's atmosphere. Pressure becomes density. Stars grow sparser. Gas disperses. Dark matter seeps into invisibility. At the center, stars crowd tightly, millions per cubic light-year. Around the sun's neighborhood, there are roughly 10. Farther out, 1 per 10 light-years. Venture farther still, and the density falls to 1 in 1,000 cubic light-years, then 1 in 1,000,000. Eventually, you reach regions where single stars drift alone, orphaned remnants ejected by encounters or collisions. Are they still part of the Milky Way? The answer depends on definition, and on where you choose to draw a line that nature refuses to draw for you. The dark matter halo only deepens the ambiguity. It stretches far beyond the last star we can see. At least 250,000 light-years, perhaps 400,000, maybe more. Some simulations reach as far as 600,000 before the halo merges invisibly into the background of the cosmos itself. At some distance, even gravity fades into the quiet hum of the universe. Dark matter pervades everything, even the vast gulfs of intergalactic space hum with its faint presence. The transition from galaxy to emptiness is not a boundary. It's a blur, a gradient without edges. Gas clouds only complicate the picture further. The Milky Way exhales matter in colossal winds, driven by supernovae and stellar eruptions. That expelled gas can travel hundreds of thousands of light-years before dissolving into the void. So, is it still part of the galaxy? Technically, yes, it came from here, and much of it will fall back one day. But for now, it floats far beyond any sensible definition of our borders. The Magellanic Stream captures this contradiction perfectly. A 600,000 light-year ribbon of gas torn from the Magellanic Clouds, no longer theirs, not yet ours, suspended between origins and futures. A river of matter adrift in the intergalactic tide. Satellite galaxies make the idea of boundaries even murkier. They have stars, structure, and shape of their own, but they orbit inside our gravitational dominion, fated to be absorbed. Are they separate or part of the Milky Way already? Both answers are true depending on the context. The virial radius attempts to impose order on this chaos. It defines the distance where gravity binds an object firmly to its host. Inside, everything orbits together. Outside, things drift freely. For us, that radius sits around 250,000 light-years, a number that looks satisfyingly clean in equations, except nothing in reality is that clean. Even beyond this line, gravity persists. We can measure it, faint and stretched thin, but never gone. The gravitational field of the Milky Way fades gradually, never fully reaching zero. Light behaves the same way. Every photon that has escaped our galaxy continues outward forever, carrying information about us across the universe. In that sense, the Milky Way's influence is infinite, gravitational, and luminous, etched into the cosmos itself. Every star that ever shone here left a whisper in the dark, a tiny imprint still traveling through eternity. When we measure the galaxy's size, we are really choosing a philosophy. The 200,000 light-year figure rests on one definition, the virial boundary, a reasonable, defensible choice, but hardly absolute. Another astronomer might select a point where stellar density drops below a certain threshold, or where dark matter thins to insignificance, or where satellite orbits lose coherence. Each approach yields a different measurement. None are right, none are wrong. The cosmos does not care for our categories. Its matter is continuous, its laws smooth and unbroken. We live in a galaxy that dissolves quietly into nothing. No walls, no edge, just a slow fading from density to void. That faint transition hides a darker truth. The Milky Way's growth was never gentle. It is a cannibal. Our galaxy built its bulk not through slow accretion but through violence. Hundreds of smaller galaxies have fallen into its gravitational maw, torn apart and consumed. This is how great galaxies live. The massive devour the small in endless gravitational hierarchies. Survival of the densest. Evidence of these ancient feasts stretches across the sky. Streams of stellar debris coil around the Milky Way like ghostly scars. Each delicate ribbon marks the remains of a galaxy that ventured too close. Its stars stretched into luminous tendrils as it was shredded by tidal forces. Presently, the Sagittarius dwarf lies mid-meal, disintegrating as we watch. Its 400 million stars will scatter through our halo over the next billion years. Eventually, only their motions will betray where they came from. But this is only the latest of many. 10 billion years ago, our galaxy collided with a rival nearly a quarter of its size, Gaia Enceladus. It wasn't a minor skirmish, it was a catastrophic merger. Both systems were ripped and reassembled, but the Milky Way endured. The Gaia spacecraft uncovered the fossil evidence, billions of stars moving on tilted, chaotic, retrograde orbits, utterly distinct from native trajectories. Chemical analysis confirmed their alien origin. Stars lighter in metals, forged in environments unlike our own. Those remnants still orbit today, silent survivors of a lost world. Before that came Kraken, an even older encounter 11 billion years past. Kraken may have been half the Milky Way's mass at the time. That colossal impact reshaped everything, igniting tremendous waves of star formation and forging much of the galactic disk we live in now. Its remnants are too well mixed to identify easily, but its fingerprints occupy every quadrant. Other victims followed: the Sequoia dwarf, the Helmi streams, and Omega Centauri, a dense globular cluster that may once have been the heart of a devoured galaxy. Each adds another layer to our composite identity. Over 13 billion years, the Milky Way has feasted relentlessly, doubling and redoubling its mass, building an empire from the corpses of lesser systems. Even today, the process continues. The Magellanic Clouds edge closer, leaking gas and stars, soon to be drawn in completely. Sagittarius disintegrates as we speak. In time, Andromeda will follow the final union, the meal that ends all meals, fusing two galactic heavyweights into one immense elliptical titan. Galactic cannibalism explains the universe's inequality. The rich grow richer. Greater mass means greater reach, and deeper reach draws more prey. Gravity turns growth into acceleration. The strong feed faster, growing ever stronger. Dwarfs, by contrast, endure perilous lives, haunted, pursued, consumed. Most will not survive unmerged. The Milky Way reigns supreme in our local domain precisely because it has eaten nearly everything within reach. And yet, the ghosts of those galaxies remain. Their stars linger, orbiting unseen among ours. Their elements fill our own bodies. The iron in your blood, the carbon in your cells, they might have been born in stars that once belonged to a different galaxy, under a different sky. You are, in part, the product of cosmic assimilation, the offspring of alien suns consumed long ago. We are the children of a galactic empire built through destruction. Astronomers find no joy in realizing their models are wrong, not from pride, but from the daunting reality of rebuilding entire frameworks. The James Webb Space Telescope forced precisely that reckoning. Launched in December 2021, the $6 billion observatory, 100 times more powerful than the Hubble, was meant to gaze back toward the beginning of time, to witness the birth of the first galaxies. No one expected it to rewrite our understanding of our own. Webb's infrared eyes pierced dust with ease, revealing what optical telescopes could never see. The far side of the galactic disk, the hidden center, the obscured outskirts. What it found stunned the scientific community. The Milky Way's faint regions weren't empty. They teemed with stars. Where we expected darkness, Webb saw billions of hidden suns shimmering in the infrared. It also turned its gaze toward our companions. The telescope resolved individual stars in small satellite galaxies with unprecedented clarity, tracing their ages, orbital motions, and chemistry. Feeding that data into galactic simulations, researchers refined our models of the Milky Way's gravitational field, and every iteration pushed our boundaries outward. But the real shock came from the stars beyond. Webb observed faint tidal streams more distant than any previously detected, some 200,000, even 250,000 light-years from our center. Such structures should not exist if the galaxy was as small as once believed. Their presence proved otherwise. They orbited within an unseen mass far vaster than our visible disk. Then came the decisive evidence: gravitational lensing. Using Einstein's equations, scientists measured how the Milky Way's bulk bends the light of faraway galaxies. Webb's sensitivity allowed unprecedented precision. The verdict: a total mass approaching 4 trillion solar masses, perhaps more, triple the textbook value. It was irrefutable. Independent instruments confirmed the result through multiple methods. Data conquered doubt. Conferences erupted in debate, traditionalists clinging to long-held estimates, others embracing the new weight of evidence. Slowly, the consensus shifted. The Milky Way, it turned out, wasn't merely big. It was colossal. But Webb's revelations didn't stop there. Its long gaze reached outward, repeating the test on Andromeda, Triangulum, and spirals billions of light-years away. Everywhere, the story was the same. Measurable galaxies were larger than recorded. The flaw was systemic, spanning the entire cosmic order. We hadn't just misjudged our place, we'd misjudged the scale of galaxies themselves. The consequences are still unfolding. Cosmological models must be rewritten. Galaxy formation theories require reinvention. Every distance calibrated by brightness must be rechecked. One telescope, one leap in capability has sent shockwaves through every branch of astronomy. It is humbling and it is thrilling, because this is how science lives, by discovering that it has been wrong and choosing to begin again. Data doesn't care about comfort. When evidence disagrees, science must rewrite itself or risk staying wrong forever. The James Webb Space Telescope forced that reckoning. It showed that the Milky Way is far larger, heavier, and more complex than we ever realized. Its scale still unfolding with every observation. Webb's findings also shook a deeper mystery: dark energy. This invisible force drives cosmic expansion, yet we barely understand it. Bigger galaxies contain far more mass, which should slow expansion, but the universe's acceleration remains constant. Either dark energy is stronger than we thought, or our model of the universe is flawed. Larger galaxies unsettle every cosmic calculation: dark matter ratios, galaxy clustering, even the Hubble constant. The very framework of cosmology still works but trembles slightly at the edges. Dark energy and dark matter might be connected, two expressions of one deeper unknown. For now, we say the Milky Way spans about 200,000 light-years, perhaps 250,000. That number will change. Future telescopes like the Roman and extremely large telescope will refine it. Each new survey tightens the measurement, but none will make it final. The galaxy keeps evolving. Our knowledge keeps chasing it. We live inside a structure too vast to see completely from within, twice as wide, 3 times the mass, for 100 billion stars and billions of worlds. The Milky Way isn't just bigger than we imagined. It's proof that we've only begun to understand our home. For now, 200,000 light-years is the best answer. Tomorrow it will be better.